Three, two, one, let's go. So, what exactly are we going to be doing today? Well, we know how to solve any separable differential equation. We know how to solve any linear first order differential equation. There are other ones out there. So today, we're going to learn how we can solve another class of first order differential equations. Okay, now we're going to have to do some setup and to get to the point of solving them, so let's do that. So recall that every first order DE can be written like this. Basically, you just isolate the derivative as a first order differential equation, so precisely one derivative shows up. So what you would do is then take everything that isn't that derivative and throw it to the other side of the equation, right? It's a differential equation, so it's an equation with a derivative in it. So isolate the derivative. Wait, and on the right-hand side, we'll have a bunch of terms that involve the independent variable x, but will also involve the unknown function y, potentially. So it's a function of two variables, and this may or may not be your first encounter with such things. Now, every first order DE can be written like this, and now there's another way to write it that is going to make a lot more sense today why we would write it in this way. So I'm going to do some things. Classic math move of, I'm just start doing stuff, and it's not going to make any sense until it makes complete sense and is completely the right thing to do. Happens a lot in math. Even like when you're doing like hardcore math research, sometimes you're just like, let me just try this. I think this might work, and you have an idea of why. So, right, the left-hand side is a fraction. I'm going to make the right-hand side a fraction. That's a thought. Who knows if it's useful, but it's a thought. And then it's like, well, I'll make it negative. Why not? Who cares? Do whatever you want. It's fine. Anyway, so if we write the right-hand side as a fraction, which not too surprising because if you're isolating dy dx, it's very possible we had to divide something. So that's pretty reasonable. So we've got this. Now, if I cross-multiply and then add, okay, the negative now makes sense. And turning into a fraction then, okay, all kind of cleans up, because now we've got this right here, and this is known as the differential form of a first order DE. So every first order DE can be written like this, and then from there we can do some maneuvering and get it in this form, and this is known as its differential form. And there should be triggering memories out of Calc 1 when you talked about differentials. So, anyway, the goal for today is to talk about DEs in differential form. There's a slick way of solving them. Sometimes. So we'll get into that. But in order to really be able to pull off that maneuver, we need to steal some ideas from Calc 3. So if you've taken Calc 3 before, great. Everything I'm going to talk about is old hat. If you haven't, though, don't worry. We're not going so deep into Calc 3 that we're going to have to spend a lot of time going off the deep end. Just some basic ideas. So Calc 3 is all about calculus in 3 dimensions, and really what that means is doing calculus to functions that have more than one variable. Right? We've just discussed that in differential equations, functions with more than one variable, well, they just show up. So shouldn't be too surprising that with differential derivatives, that we have functions with the variables, and we're going to want to take the derivatives. And so how do you do that? Well, you could take its derivatives with respect to each of its variables. So the partial derivatives are precisely what I just described. You take the derivative with respect to one of the variables and leave the other ones constant. Right. So for example, here's a function of two variables, y cubed plus x cubed times y squared plus sine of x times y plus e to the negative x. All right. Well, if I take the partial derivative, so note the fancy D to represent partial derivative. If I take the partial derivative of that with respect to x, well, what's going to happen? In the eyes of x, y is a constant, so this gets killed. In the eyes of x, y is a constant, so this is really a constant times x cubed, so you take the derivative as normal. You take the derivative of x cubed, 3x squared, and y squared goes on for the ride. Derivative of sine of x is cosine, y is a constant, goes along for the ride. E to the negative x, derivative goes as usual. And the same is true for the partial of this function with respect to y. This is y, derivative goes as usual. x cubed is a constant, goes along for the ride. Sine of x is a constant, goes along for the ride. Function that only involves x gets killed by the derivative, because in the eyes of y, x is a constant. Okay, so that's all there is. There you go. That's how we take the derivatives. It's literally what you would think if you've never seen it before. You have multiple variables. Well, just take the derivative with respect to one of the variables. Ignore all the other ones. So that's literally it. Nothing special. All right. So like the derivative measures rate of change, partial derivatives also measure rate of change. But note that this measures rate of change with respect to x, and this represents rate of change with respect to y. So if we wanted to get the full out rate of change of the function, well, without going too far into it, it involves some vector maneuvering and some things like that. The differential of a function of two variables, which measures the rate of change of f, similar to how dy f prime dx measures the rate of change of f. The differential here is this quantity right there. So note now there is a summation going on, and again, there's a vector reason for that involving dot products, but we don't need to go that far, but it's there. But anyway, so this measures the rate of change of our function, right? Our function has two variables, so we can measure them independently to measure the change with respect to x, the change with respect to y, and then to get the full out change, this turns out to be the right quantity to look at to get it, similar to how f prime fills that role in the one-dimensional case. So for example, if we've got this function of two variables right here, then its differential, measuring its overall rate of change, would be this quantity right here. So take the derivative of this with respect to x, that's that right there. Take the derivative of that with respect to y and put it right there. There we go. And hey, you may not notice it, but your brain does. That looks real familiar, like, oh, I don't know, the differential form of a differential equation. Ooh. So, a constant function of two variables must have a zero differential. Right? It's constant, so no rate of change. More precisely, if you've got f, x, y, a function of two variables equaling a constant c, then its differential is equal to 0. And, oh, hey, doesn't that look exactly like the differential form of a first-order differential equation? Yes, it does. So, if we could find a function f so that its partial of f with respect to x lined up with m, and its partial of f with respect to y lined up with n, well, then what do we know? Oh, that would then give me implicit solutions, right? This satisfies this equation. So, if I can create such a function so that it lines up with the m and the n, that means f satisfies that, meaning that this has to then give me implicit solutions. Boom. There we go. Stole some ideas from Calc 3, and now I've got a method of solution for any first-order differential equation. Get it in its differential form, and then find a function whose partial with respect to x lines up here and partial with respect to f lines up there. All right, nice. Okay, so let's give it a go. Hey, there we go. That is a first-order DE in its differential form. So what did we just learn? Well, implicit solutions, via some ideas from Calc 3, will have to be given by a function that would satisfy its partial with respect to x lining up with this, its partial with respect to y lining up with the dy term. Okay, so hey, I've got this, I've got that. These are just begging to be integrated, right? So let me integrate this with respect to x, and now this works exactly the same way as differentiating with respect to x worked. Y is a constant, x is a variable, so y cubed, when you integrate it, will just be y cubed times x. Y squared goes along for the ride. The integral of this with respect to x would be negative cosine, making it positive. X squared goes the way you want it to, get the 2x goes the way you want it to, get in the x squared. And now note, with respect to x, there could have been a whole other function with respect to y present, right? Because derivatives with respect to x kill functions with respect to y. Okay. And a similar story for the partial of f with respect to the partial of y. If you integrate that out with respect to y, you'll get this. Note the unknown function in terms of h showing up. So we have two equations, two unknown functions, but there's good news. Y cubed x matches this. Y squared cosine matches that. X squared would then have to match the h of x. G of y would then have to match the negative 4y. So that allows me to match the terms. So that means the function f is precisely this one right here, the mystery terms we were able to match and solve for. Now remember, this is not the solution. The solution, the implicit solution to the differential equation, is then this equal to a constant. Because remember, the trick we're using from Calc 3 is that the way to measure the rate of change of a function of two variables is to use its differential. If your function is constant, its differential is 0, which makes it look exactly like the differential form of a first-order differential equation. So it's not that f is equal to this is the answer. This equal to a constant is the answer, right? Because we want this function f to have a 0 differential, and the only way that happens is if it's constant. And there we go. Nice. So that is a real slick move. So take your DE, write it in differential form, find a function f so that the partial with respect to x matches here, and the partial of f with respect to y matches there, and then boom, done. Solved. That's it. Go home. Why are you still here? Oh, you are home. Probably watching this. I am. I'm recording this in my bed. Real classy. I got a coffee and I got my daughter left like stuffed animals and things in her bed, so I'm just chilling. All right, nice. Well, naturally you must say, well, this seems too good to be true, right? I just solved the differential equation, and it feels a little like magic. It feels like I really didn't do anything, right? So naturally, you're going to ask, okay, well, is this it? Has differential equations been solved? Well, I rigged that example we just looked at. That example was rigged to work. Right, consider this, for example. Hey, it's in differential form. Just do the exact same method. So set this piece equal to the partial of f with respect to x. Set this piece with respect to be f with respect to the partial of y. And again, remember, we're doing this whole thing because we're trying to make this look like the differential of a function of two variables. And then once we figure out what the function of two variables is that matches that, then it equal to a constant would be implicit solutions. And before we even get into it, you should immediately be very wary of the method, because it doesn't seem like it's going to go as nicely as it did last time, because when I do my integration, things are a lot more wild this time. So the mystery function with respect to x that showed up, that matches up with this one right here. The mystery function with respect to y that shows up matches with here, but this term and that term do not match. These are never equal to each other. Right? I mean, there are some choice values of x and y that you can go with that would make them line up, but they don't always equal each other. So such a function literally does not exist. Okay. So that means the method does not always necessarily work. So then, of course, well, if it doesn't always work, we just saw it worked, and we just saw an example where it didn't work. So that makes it interesting, right? We verified that, okay, well, it works sometimes and doesn't work other times. That's worth investigating and studying. Right? If it works all the time, well, that's great. And if it never works, well, then that's crap. So this lands in the interesting zone, where sometimes it's going to be good and other times it's not going to be. And for those of you who have taken Calc 3 already, hopefully you're recognizing what's going on. I'm trying to find the potential for a conservative vector field. But, yeah, if you haven't, then those words don't mean anything to you. Don't worry. When you take Calc 3, it all makes sense. It'll be great. Okay. So, when is it going to work? So, suppose we do have a first order DE so that it does work. That means we found the function f that satisfied that its partial respect to x was m, and its partial respect to y was n. Well, then what's true? Well, if I look at what are called the mixed partials, then this had to have happened. If I take the derivative of m with respect to y, then I've taken the derivative of f with respect to first x, and then with respect to y next. Similarly, if I take the partial of n with respect to x, then I'm going to take the partial of f with respect to y, and then I'll take the partial of that with respect to x. So it turns out that for the functions we care about, this equality is always true. So the order in which you do it does not matter. These will have to coincide. There are these known examples where this doesn't hold, but they're always like functions that don't have nice differential properties. And right, we're in differential equations, so we want our functions to have nice derivatives. So for our class, this is always equal. In general, not true, but that's pathological nonsense, and only math people care about that. So, and this is not a math class at all. Are you kidding me? Anyway, so we're going to call a first-order differential equation exact when the partial of m with respect to y, note the opposite one, lines up with the partial of n with respect to x, note the opposite variable that it's attached to. And these are the ones so that the method we just learned works. So these are the exact ones that we're happy with, I guess. You can roll your eyes at that. Okay, so let's reconsider the two examples we looked at and check them for exactness. Okay, so take the partial of this with respect to y and take the partial of this with respect to x, and hey, you get the same thing. So that DE is exact. Now, the one where the method didn't work, note that the partials don't line up. So it's not exact. And like I said, the exact ones are precisely the ones that the method is going to work, right? The method hinges on such a function f existing. If you can't have these line up, then that function cannot possibly exist, right? You're going to have these terms that just don't line up. Okay. So, with all of this said and established now, let's actually solve a DE. Okay, so here we are again. Time for you two, if you haven't yet, pause the video and give it a go. We just discussed the new method of solving this. So take a minute, try it out on your own, and then come back and we'll see how it goes. Okay. That's time for me to cough and clear my throat. I don't know. I shouldn't drink coffee while I do these, right? I should be like drinking like tea with lemon or something to have a smooth voice. And don't burp or, whatever. I haven't sneezed yet while I've recorded. That's impressive. So, that's good, I guess. I played, I'm just rambling now at this point. Are you working on the problem? You should be. Anyway, I was in a band in college, and I always ask my bass player, like, what happens when you, like, sneeze when you're playing? What do you do? And he's like, I just hold it in, man. And I'm like, I can't even do that. So, like, there'd be, like, times when I was playing, and I just, like, sneeze and screw up, and I was like, nobody's even listening to me. It's fine. I don't need to worry about it. Anyway, yeah. So, okay, another one. Let us solve this. Alright, let's do it. Okay, so first things first, you see a differential equation in differential form, check for exactness. If it's exact, then the method we just learned is going to work, and it's going to be great. If it's not exact, that doesn't mean it can't be solved, it just means that we have to use a different method. But, right, we're trying out this new method, so we're getting used to it. So here we check for the exactness, and ta-da, it is indeed exact. Okay, so that means that our function f, the one whose partial with respect to x and partial with respect to y match the dx and the dy term, respectively, will actually exist. Right? This check for exactness ensures that when we do the integrations, right there, the terms that involve multiple variables match each other. And the terms that involve single variables either match each other or will match the mystery functions that will appear via the integration. Okay. So here we see the y log x that matches, the x 3x squared matches the h of x, the negative 2y matches the g of y, and ta-da! There we go. Solutions are implicitly given by this function right here. So we match g of y and we match h of x. And hey, there we go. Now, am I done? Not exactly. I have an initial value problem here, so I got to plug in that initial information. Now, how do I do that in this case? Okay. So, remember, when we say y of 1 equals 6, what we mean is that the solution to my differential equation will pass through the point x equals 1, y equals 6. Right. So if you input 1, the input is x. When x is 1, y is 6. So if we plug that in, we'll find that c has to be negative 9, and thus the unique solution in its implicit form is given as such. And it is actually worth noting, this is one of those cases where, even though this is an implicit equation, you could make this explicit if you wanted to. This actually isn't that bad. I would add the 9 over, add the 2y, subtract the y log x, factor out y, and then divide over the, what would it be, 2 minus log. Yeah, that would work. But anyway, there we go. That's the exciting world of the method for exact differential equations. Okay, cool stuff. Hope you liked it. I'll see you next time.